Welcome to PM Ready, your guide to becoming PMP certified. This is the lesson on quality tools, part 3. A Pareto chart is based on the Pareto principle, also known as the 80-20 rule. The Pareto principle was introduced by Joseph Girard, who named it after the Italian economist Vilfredo Pareto, who showed that about 80% of the land in Italy was owned by 20% of the people. It turns out that the 80-20 rule applies in all sorts of circumstances. It's not always 80-20, it can be 70-30 or 90-10 or whatever. But the idea that most of the effects come from a relatively small number of causes comes up quite a lot. In sales, they say that about 80% of the revenue comes from 20% of the customers. In software, 80% of the people only use about 20% of the features. Or, to put it another way, 80% of the value of the software comes from just 20% of the features. This has some interesting implications about where and how to focus project funding on software development projects. But that's another subject. I worked at a large organization that had its own call center for IT issues, and they did a Pareto analysis and found that a large percentage of the calls that they were getting were to reset passwords that had been forgotten. When they discovered this, they launched a project and developed an internal online tool that users could access on their own to reset their passwords. This dramatically reduced the number of calls to the call center. Pareto analysis identifies a problem, identifies the causes, groups these causes into logical groups, counts the number of occurrences of each cause, and graphs the result using a bar chart, with the most common causes on the left. A red line is sometimes added that sums up the bar charts from left to right. If amounts are shown as percentages of the whole, with the vertical axis going from 0 to 100%, as in this example, the bar charts will add up to 100%, and the red line will grow as it adds these up until it reaches 100%. A histogram is a great way to visualize and analyze and communicate data. And it's a first step to understanding and using statistical process control. This histogram is an example that shows how long it takes to load a particular web page. It's based on taking hundreds of measurements and then grouping these measurements into ranges or bins. This histogram has a bin for 0 to 99 milliseconds, 100 to 199 milliseconds, 200 to 299 milliseconds, 300 to 399 milliseconds, and so on. Each bin is 100 milliseconds wide. It shows that the page never loaded in less than 200 milliseconds, that 10 times it loaded in between 200 and 299 milliseconds, that 50 times it loaded in between 300 and 399 milliseconds, and so on, and that it never took longer than 1,800 milliseconds. By graphing the count or frequency on the vertical axis, you can see the overall picture, or what is called the distribution of load times. You can see that it rises steeply, peaks relatively early, and then tapers off to the right. You can use a histogram to see the distribution of numerical data, such as web page load times, or the number of defects found per day, or the number of parts manufactured per day, or the revenue per day, or just about anything that can be measured over and over again, or for which you can take samples or measurements from a large number of items. It can be used to analyze your process outputs, identify quality issues, and you could compare histograms from day to day or week to week, etc., to see how things are changing over time and do some trend analysis. You can also compare multiple processes to each other, such as comparing one production line to another, or one project to another, or an old process to a new process. And it allows you to communicate a lot of information quickly. Rather than just communicating the range of measurements, or the average, or the peak, you can see the whole picture, the distribution, at a glance. This histogram has a characteristic bell shape known as the normal distribution. The normal distribution isn't what you normally see for all processes, but it's a nicely shaped symmetrical distribution that is common in many situations. And it lends itself well to some of the more basic statistical process control methods. Different shapes of distributions can mean different things, and sometimes it's natural for that process and sometimes it's not. You might expect to see a normal distribution like this one when measuring key quality parameters in, say, a manufacturing process, such as the diameter of a ball bearing. Assuming the process is functioning well, the peak of this distribution might be right where our target diameter is, while the other bars to the sides indicate tiny variations in this diameter. Variations that are so small that they're all acceptable, but the difference are measurable, with some being a tiny bit smaller and others being a tiny bit larger. And the farther you get from the target, the fewer ball bearings there are with these greater and greater variations. The width or range of values in your histogram depends on how much variation there is in the measurements, or the process, or whatever it is that you're graphing. It can also depend on the width of the bins that you choose to use for your histogram. A normal distribution can be a tall, skinny bell shape, or a medium one like this one, or a short, wide one. But all normal distributions have this characteristic symmetrical bell shape. This histogram has what is called a skewed distribution. This is a natural distribution that you would expect to see when there's some sort of natural limit, in this case on the left-hand side. For example, this could represent the number of defects found per 1,000 lines of code. You naturally can't have fewer than 0 defects, so that's a natural limit. This skewed distribution would indicate that it's common to have a few, but rare to have many, but impossible to have less than none. By the way, notice that this demonstrates the Pareto principle. Most samples of code have few defects, and only a few have many defects. A skewed distribution is also natural for measurements of time, in which 0 is the starting point, such as when measuring the duration of support calls. They all take some time, so the distribution has a natural limit of 0 time on one end, with most calls not taking too long, but some taking noticeably longer. This was also the distribution of our example of web page load times, again because of the natural limit on the left, that it takes at least a certain small amount of time at a minimum. Here's an interesting distribution known as a bimodal distribution. It looks almost like two histograms combined, and that may well be exactly what's going on. If the data you're using comes from two processes, or two work shifts, or two sources of raw materials, or two different production lines, then you can get a bimodal distribution like this if there are differences between these two data sources that affect the measurements. Usually, you won't know that you have two different data sources. You'll think you have just one, but when you see a bimodal distribution like this, it tells you that you probably do have a couple of different data sources embedded in your data, and you need to figure out what they are. You can do this using a technique known as stratification, which we'll get to later in this lesson. By separating these two histograms and understanding where the different sources come from, you can compare these processes and compare the quality of these processes and use this information to improve your quality control. What happens if you have more than two histograms merged together? What if you have 3 or 4 different data sources mixed together and you don't know it? Then you end up with a multimodal histogram that has 3 or 4 peaks or more. If you have a histogram that looks like this, it could mean that you have multiple processes, work shifts, sources of material, production lines, measurement techniques, and so on, all contributing to making a multimodal histogram that looks more like a mountain range than a bell. Or it could mean that your sample size is too small, that you don't have enough measurements for the histogram to really take its true shape. Or it could mean that your bins are too small, and you need to try making them wider and see how it looks. But the only way to know for sure is to use stratification to see if the data separates based on different data sources. A histogram with an edge-peak distribution can have a normal distribution like this one, or any other type of distribution, such as skewed or bimodal. But what's characteristic about an edge-peak distribution is that it has a peak on the far edge. It's always on the very edge, but it can be either the far right or the far left. How does this happen? Well, suppose you had a survey that asked project managers how many projects they've managed, using a multiple choice question with answers 0, 1, 2, 3, and so on, up to say 10. And then the last option was more than 10. That more than 10 option would likely generate an edge peak when you display this data using a histogram. Or you may be displaying the average gas mileage of new cars and have bins that are 5 digits wide, 0 to 5, 6 to 10, 11 to 15, and so on, but then ending with greater than 40 miles per gallon. This would also create an edge on the histogram. Or if the data started with less than 10 miles per gallon, it would create an edge on the left-hand side of the histogram. Although this can happen with any type of histogram, it's especially common when you have a skewed distribution, and you artificially group all the tail data into a single bin, such as with call center data, having a bin for calls that last more than 2 minutes, or web page load times longer than 3 seconds. A comb distribution looks like a comb, with every other bar being significantly shorter. The bars alternate between tall and short, but each set of tall and short bars seem to form their own histogram, a tall one and a short one, interleaved. This can be caused when different people use different rules for rounding the numbers. If people reported their height in inches, and most rounded to the nearest inch, while others rounded to the nearest half inch, and you had bins that were half an inch wide, then you'd end up with a comb distribution something like this one. On the other hand, if you had bins that were 1 inch wide, then you wouldn't have a comb distribution, because all of the half-inch measurements would be grouped into bins with the full inch measurements, so the comb wouldn't show up. If everyone reported their height rounded to the nearest inch and you created a histogram with half-inch bins, then you'd end up with a comb distribution that, instead of having alternating short bars, has alternating blanks. You could end up with a comb distribution either because of the way you gather the data or because of the way you group it. If your bins are smaller than the data you have available, you'll end up with a comb. For example, if you use published numbers for gas mileage, which are all rounded to the nearest mile, and you put that into a histogram with bins that are half a mile wide, then you'll end up with a comb distribution. A histogram with a truncated distribution is one which looks like one or both of the sides have been cut off. It could be any type of distribution, but if it appears to be artificially cut off on one end or the other, or both ends, then it's known as a truncated distribution. Suppose you have a supplier that provides you with ball bearings, and when you measure the diameters, you end up with a truncated distribution like this. It's probably because the supplier's manufacturing process isn't good enough, and a fair number of the ball bearings produced don't meet specifications. So the supplier has to inspect each one and remove the ones that are outside of the specification limits. The histogram doesn't show bars for these because they have literally been removed from the batch that was sent to you. This has traditionally been the case in the manufacture of microprocessor chips for computers. Because manufacturers are always pushing the limits of what can be done to create faster and faster chips, manufacturing processes can't reliably create these chips. And a fair number of them fail to meet these extreme specifications. And what happens to the edges or tails of a distribution when you cut them off? They can show up elsewhere, in a tails distribution. A tails distribution can have just one tail on one side or the other, or on both sides, like this one. This could represent the ball bearings or microprocessor chips that didn't meet specifications. If you receive raw materials or parts that have a distribution like this, it probably means that someone else purchased the best ones and you got the leftovers, the scraps. They may still meet your specifications, they just didn't meet someone else's. For example, when I go to the lumberyard or home improvement center to get some 2x4s for a project, I often find that they've been picked over, and the best, straightest 2x4s have been taken, and the most bent, twisted ones have been left behind. Sometimes I also need straight 2x4s, so I'll also pick through the pile to find the best ones. Other times, it doesn't really matter for what I'm doing, so I can just take the leftovers. Years ago, when I was going to university, I read about an ingenious use of leftovers. The article was about a guy who bought thousands of rejected microprocessors for pennies on the dollar. He used some software to diagnose them to determine exactly which specific functions each microprocessor failed at, and which ones it worked properly at. Then he put them all together to create a massively parallel processing computer, and used software he'd written to automatically avoid sending specific tasks to processors that couldn't handle those specific tasks. The system played to the strengths of each individual processor and avoided the weaknesses of each individual processor. By doing this, he was able to create a powerful, reliable computer using reject parts. A real-life example of the old saying that one man's trash is another man's treasure. When you create a histogram, you need to decide on the width or range of your bins. If the data ranges of your bins are too wide, then you'll end up with too few bars in your histogram, like the one on the left, and you won't be able to see the distribution. If the data ranges are too narrow, you'll end up with too many bars, like you see here on the right, which will also make it difficult to see the distribution, because you may have peaks and gaps that obscure the big picture, because you're basically looking too closely at the data. If you pick a good range for your bins, you'll end up with a histogram that clearly shows the distribution, like you see here in the middle. You should experiment with different bin sizes until you come up with a size that works well for the data. How many bins you need will depend on the data, but you might start with about 15 bins that capture all or nearly all of the data, and then adjust from there, changing it to have a few more or a few less, and then just continue adjusting until it looks good. And this concludes part 3. PM Ready is a publication of PM Guaranteed and is based on the Project Management Institute's PMBOK guide.